So let's do example 1 where we try to apply the squeeze theorem to prove something. So our example 1 from section 2.6, we want to show the limit as x approaches 0 of x times sine of 1 over x is equal to 0. So we're looking at the limit as x approaches 0, x times sine of 1 over x equals 0. Now, our goal is to construct a upper function and a lower function. So we need to construct an upper and a lower function that we're sure that this x sine of 1 over x is stuck in between. And this is going to be slightly tricky to do. Let's see here. So first of all, I'm going to say, if we just look at sine of 1 over x. And if we think about sine of whatever is in here, the biggest number sine can give back is 1, and the smallest number sine can give back is negative 1. So we know sine, it's always bigger than or equal to negative 1. So it can get negative as up until it gets to negative 1, then it has to get back to positive, or has to get back to less negative. And the biggest value sine will return is positive 1. So if you have a trig function in this like sine or cosine, you know sine and cosine are bounded below by negative 1, and they're bounded above by positive 1. So I'm going to take this equation and I'm going to multiply it by x. So, well, I'd like to multiply this equation by x, but I have to be a little bit careful. I have to split this into two cases, I think. Because if x is negative, if we're approaching from the left, then I'm approaching with numbers like negative 0.001. So my x will be negative numbers. And then whenever I multiply through by x that's negative, the inequalities flip. If x is positive, when I multiply through by x, the inequalities don't flip. So let's look at x. Let's look at the case where x approaches 0 from the left. So if x is approaching 0 from the left, then I multiply this whole equation through by x. The inequality directions flip, because when you multiply an inequality by a negative, the direction of the inequality flips. And what I get out here is if we're approaching 0 from the left, then negative x is bigger or equal to x times sine of 1 over x. And that's greater than or equal to x. So x itself is the lower bound, and negative x is the upper bound. So x will be negative, and the minus a negative will be positive. Okay. Now if x is approaching from the right, if we approach 0 from the right, we're letting x be numbers like positive 0.001. So x is a positive number. And then when we multiply our inequality by the x, the inequality direction doesn't have to switch. Okay. So x is now positive because we're approaching 0 from the right. So we get negative x is less than or equal to x sine of 1 over x is less than or equal to x itself. Okay, so let's try to put these together. There's a couple ways to do this. Let me think. So if x is negative minus a negative x, okay, basically here's what we need. We need something.
Pardon the interruption. We just want to let everybody know that we will have our second round of buses ready and out there waiting at 3:45. Thank you.
Okay, so we need something that when x is negative, so we're going to try to build the upper function here. So x sine of 1 over x is bounded above by negative x when x is negative, and it's bounded above by positive x when x is positive. So for the upper limit, so let's write upper, for the upper function, we need something that when x is negative returns negative x, which will be positive. So if you have a negative x, it returns minus, and then the x is also negative, so minus a negative x would be the positive value. And when x is positive, leaves x alone. So we're looking for a function that basically, if you have a negative number, it returns the positive value of that. And if you have a positive number, it leaves that positive number alone. So what that actually is absolute value of x. So our upper limit, f of x, sorry, not f of x, u of x, our upper limit, u of x, will be absolute value of x. Because absolute value of x returns negative x when you're negative. So if I put a negative 7 in there, it gives me back positive 7. And if I put a positive value in there, like positive 3, absolute value of positive 3 gives me back 3. So for the other side, now we need to say, okay, that's great for the upper limit. We can use absolute value of x. That kind of combines these two things together into a single one. What about the lower function? So we say, okay, well, we need something now. Let's see what happens. So when x is negative, it returns just a negative x. And when x is positive, it makes x negative. So we need something that when x is negative, it returns the positive value. Whoops, no, just kidding. So when x is negative, it returns a negative. Returns x itself, which is negative. And when x is positive, it returns, so if you have a positive x, it returns negative. It returns negative of that. X is positive, it returns negative x, which is positive. So basically, what we want the lower function to do is if you have a negative number, it leaves the negative number alone. And if you have a positive number, it returns a negative. So the lower function, if we think about it a little bit, is going to be negative of absolute value of x. If I put a negative number in there like negative 7, absolute value of negative 7 is positive 7, but then it gets made negative. So negative 7 gets left alone and just stays as negative 7. If we put a positive number in there like positive 3, well then absolute value of positive 3 is 3. The extra negative makes it a negative 3. Whoops. Sorry, this shouldn't be positive, I'm sorry. X is positive minus a positive will be negative. So basically this one here, if you input a negative, you get a positive back. If you input a positive, you get x, it leaves it alone, which means that it's still positive. So that's your upper one. Your upper one always returns positive. This lower one, if x is negative, it leaves it alone, so you get a negative back. If x is positive, then it gives you the negative back, which is a negative. So these will be our bounding functions. So now what we can say for starting to build the squeeze theorem is we know that we have the lower function of absolute value of x is our lower bound. That is less than or equal to x times sine of 1 over x. And that's less than or equal to our upper function, absolute value of x. And we know that that's true because we proved that since sine was bounded between -1 and 1, we could multiply sine by an x less than 0, and that generated this inequality. And then we multiplied sine by an x greater than 0. That generated this inequality. And then we were able to look at the upper, like if you look at x sine of x, what's the one that's greater than it? And we saw for x's approaching 0 from the left, so for x negative, we get back minus a negative x, which is positive. And for x approaching 0 from the right, we get back just x itself, which is positive. So we always got back positives. And for the inequalities, for the value that is less than the x sine of x in both cases, when x was approaching from 0 from the left, so it's negative, it gives you back the negative x. And when x approaches 0 from the right, so it's positive, it gives you back negative of a positive x, and minus a positive is negative. So the red ones would always be negative. So, okay, that's the first part of the squeeze theorem. If we go back up to squeeze theorem, the first part is verifying that you have this inequality here set up. So we did all that work, and that just got us the first part here. Next, we need to show, does the limit as x approaches c of the lower function and the limit as x approaches c of the upper function, do they approach the same thing? So that's our goal next. Well, let's think about what does the graph of negative x look like, or negative absolute value of x. Negative absolute value of x, if we think about it, it's absolute value function with an x-axis reflection. So it'll be kind of a upside down v. And we can see from this graph, as we approach 0 from the left, the limit as x approaches 0 from the left is 0, and the limit as x approaches 0 from the right is 0. So the limit of negative absolute value of x as x approaches 0 is 0. Remember, from our problem statement, we're trying to show the limit as x approaches 0 of stuff. So that's why I'm looking at the limit as x approaches 0 of my lower function. Then if I look at the limit as x approaches 0 of my upper function, say, well, okay, here's positive absolute value of x. The limit as x approaches 0 of that, yes, let me scoot that over a little bit. Regular absolute value of x just looks like a V shape, so kind of like that. And we would say the limit as x approaches 0 of just regular absolute value of x. Well, as you approach 0 from the left, as you approach x equals 0 from the left, the y values approach 0. As you approach x equals 0 from the right, the y values along the function also approach 0. So the left-hand limit approaches 0, the right-hand limit approaches 0. So this statement here that we did all that work initially to, this statement here verified that we had that. The lower function is lowest, the middle function is in between, and the upper function is the largest. Now we're trying to work on this, and I think we've just done the work to show that this is true. So if we look down here, we said, well, the limit as x approaches 0, use a different color here to kind of wrap this up. Limit as x approaches 0 of negative absolute value is equal, because that equals 0, that's equal to the limit as x approaches 0 of the positive absolute value, and they both equal 0. So that is the second part. So this right here lines up with this right here. The lower limit is equal to the upper limit, and they equal some L. In our case, the x approaches 0 of the lower equals the limit as x approaches 0 from the upper, and the actual limit happened to be 0 as well. Then the squeeze theorem applies, and we get the limit as x approaches c of the middle function exists, and it equals the same limit. So for here, we have this part. We showed that they're lined up the correct way. We showed that this is true, so we can say then, by the squeeze theorem, the limit as x approaches 0 of x sine of 1 over x exists and is equal to the same limit that these two things approached, which is 0. I'm going to write this up one more time underneath this because we kind of have stuff with some absolute values in here, so the work's kind of spread out. So we did all our work here to generate this statement. We looked at graphs to generate this statement, and then the squeeze theorem got us the final bit. So if I was really going to write this up nicely, I would say negative absolute value of x is less than x times sine of 1 over x is less than or equal to absolute value of x. If you're trying to do this in like an AP free response, you'll need to show scratch work as to why that might be true. I don't think you can just jot that down. I think they'd want to see a little bit of this stuff here. How did you come up with that? So we know that this is true, and we know from our two little graphs that we did, the limit as x approaches 0 of negative absolute value of x is equal to the limit as x approaches 0 of positive absolute value of x, and those both equal 0. So then, by the squeeze theorem, the limit as x approaches 0 of x sine of 1 over x exists and is equal to the same limit that these both approached, in this case 0. Okay, so that's if we were going to write it up. That's kind of the final writing. We have a bunch of scratch work reinforcing that that's what we want. Now the next thing we're going to do here to finish this up is let's actually graph this and see. We did all this work and stuff, and that seems great, but let's see if we can kind of see what's going on here. So first of all, let's graph what the middle function is. Middle function was x sine of 1 over x. Whoops, I've gotten that kind of weird. Okay, that looks real strange. Okay, so this is probably zoomed in a good thing where we can see it. So let's look at absolute value of x. I wonder if it'll let me type it in like that. All right, so absolute value of x is this blue thing, and we can see that absolute value of x, that does form a nice upper limit of this x times sine of 1 over x. Well, let's check negative absolute value of x. So that is this green color. I wonder if there's a way to flip the colors around. I'm going to do that real quick just to make stuff line up. So let's make that green the top one. Let's make that the x, sine of 1 over x. And then let's make the top one that was red. Let's make that the bottom function. So kind of lining this up with the colors that we used in there. The absolute value, we can see that does form a nice upper bound on our function. Negative absolute value of x forms a nice lower bound on the function, and our function is stuck in between these two. So as we approach 0, we're not sure what this blue thing's doing, but we know the green one approaches 0, and we know that the red one also approaches 0. So this blue one that's stuck in between them is forced to take the value 0 as well. And that's a nice example of how the squeeze theorem works. So I think that kind of illustrates we did all that work of finding this negative absolute value of x, x sine of 1 over x, less than or equal to positive absolute value of x. And now we can kind of see that it works. And even if, like, suppose as we go further out, like these happen to just stay lined up, we prove that inequality always kind of holds, where green's on top, blue's in the middle, and red's down below. But even if we had one of this where the blue, say, curved above the green here, or like the red bent back over and crossed over these, it wouldn't matter if that happened way out here at like 4, because we're curious about what's going on at 0. And as we scoot on in on 0, we have it's lined up the whole time. The upper function's on top, middle function's in the middle, and the lower function's on the bottom. And one more thing you may note is you see, well, hey, it looks like the blue touches the green here, and it looks like the blue touches the red there. And yeah, it does, and that's okay because this inequality has the or equal under it, so it's okay that this happens to be equal to the value. It's just it has to be bigger or equal to the bottom or less than or equal to the top. So we'll stop that example there.